Oh, wait, minus a bigger extra.
Find electric potential. Okay. So, charge sphere integration problem we saw in classwork example, we saw in a tutorial. I think you guys did it on the homework, and it's on the practice exam. So I don't know about you guys, but that sounds like an alarm that it's probably on the exam. Maybe not necessarily your version of the exam that you get. We'll see. So let's, for this one, it's just given charge Q on sphere of radius big R. Just find the electric potential everywhere. It's a sphere, so it's just going to depend on radius. There's two little situations here. We've got the inside the sphere problem, and we've got the outside the sphere problem. So we're going to solve them both. We just pick which one to start with. I'm going to start with the outside because I like to come from the outside in personally. So we've only got really one equation to work with here, not to find v of r, which is going to be the integral of E dot dl. That's, I believe, exactly what's on your equation sheet, minus from A to B. And this will give the voltage difference from A to B. So what we're going to do is we're just going to run this from infinity out to the surface of our sphere. That'll basically give us just the objective voltage, because at infinity, we know voltage falls off with distance, so it'll be 0 at infinity. So if we go from 0 to whatever the value is. So what we need is E, if we want to do that. So how are we going to get E? Well, it's a configuration of charges, so immediately it should sniff Gauss's law. So we're going to draw a surface. What shape should be the surface? It's a sphere, because it's a sphere. Just match whatever the shape is. So we'll draw a sphere of some arbitrary radius. I'm going to call it little r. And our Gauss's law is going to be E dot dA closed surface integral equals a Q enclosed with epsilon naught. Is that right? Yes, it is. Lovely. All right. Well, we know what Q enclosed is inside of our sphere. It's all of the charge, so that's just going to be Q. And anytime we do Gauss's law, we don't want to do that integral. We want to kill it off using symmetry. So we're going to do a sphere. So we're just going to make this the surface area of the sphere and count all of the electric flux that goes through it. So we can just kill off our integral. Just say that's going to be 4 pi r squared. Surface area of the sphere. Sounds right? Yeah, it sounds right. Does that give it to us? Yes. Yeah. Yes, beautiful. Times E as a function of r equals Q over epsilon naught. Lovely. I've got E. E of r equals Q over 4 pi epsilon naught r squared. So that's classic Gauss's law. You have some configuration of charge. Draw the same shape as your surface. Murderize your integral, because it's just going to be the surface area of whatever you drew, and it equals the total charge enclosed. Great. So we have electric field. In order to get electric potential, we just got to integrate that bad boy up. Keeping in mind, we're not doing a surface integral, we're doing a line integral, dl from A to B. So we're going to come in from infinity, like so, and then we're going to end at our sphere. I can't handle both of these problems in a single integral because the electric field outside we determined from Q being every bit of Q. Once we're inside, we'll only have some of the charge inside of our Gaussian surface. So it'll be a different expression for E. So I can't do it all in one step. So let's do our integral. We do our V R equals minus. I'm going to go from infinity to R. From infinity to the radius that I want. E of R dot dl. I plug that in. That is a 1 over r squared integral. So I'm going to get minus q over 4 pi epsilon naught. 1 over r squared integral is going to take us to minus r to the minus 1. So minus 1 over r. From infinity to r. Which is going to be, let's see, this guy is going to be 1 minus 1 over r minus 1 over infinity, which is 0. So this is just minus 1 over r. So we did minus q and then 1 over r, 4 pi. So not r. That equals v of r. For r greater than radius. Did I do it right? Yep, beautiful. This I think the solutions use k, but we know that k is 1 over 4 pi epsilon naught. So cool. Yes.
On the exam, could you say that like from far away it's a point charge? Because I think that's what Caleb told me.
You absolutely can, and the reason you can do it is because of Gauss's law. It only cares about Q enclosed. It doesn't matter if it's at a single point or it's a schmibble of random charge configuration. From infinity, it looks like a point charge.
So on the exam, we could just say point charge.
Yep, absolutely.
Point charge equation.
Oh. If you're given the point charge equation, absolutely.
Okay.
If you're not given the point charge equation, I would work it with the Gauss's law. If you practice this 2 or 3 times, you can do it in 2 steps. Write down those equations. You can just immediately write this down and kind of just jump to here. When I was studying for UConn exams, I think I did this problem in a variety of situations 3 or 4 times. I got it down to like 2 minutes each. Other questions on this one? All right. So we found the outside. So now we need to do inside. We're going to do the exact same thing, but we're just going to be really careful about how much Q is enclosed for our Gaussian surface. So inside, we've got a sphere, we've got a Gaussian surface we're drawing. And we know that Q is spread out over the entire volume of our sphere. So the density of charges, so I'm going to call charge density is Q in the 4/3 pi r cubed volume of our sphere. Do you remember charge density is rho? It's that P. So how much charge is inside of our Gaussian surface, little r? Well, it's going to be the density of charge times the volume that we are enclosing. So how much Q enclosed of our little r sphere is going to be charge density times the volume of the sphere, which is that's the volume of the sphere, or pi little r cubed. That should be familiar, where we end up with a Q of the ratios. Yes, Q ratios, the radii. That little r cubed over big R cubed. We've seen that a couple of times in sphere problems. I think we see it again in, I want to say problem 6, but in problem 6 they punch out the middle part of the sphere. So you end up with like a plus minus situation there because you remove a piece. But it's the same idea. Lovely. So then we're going to run the exact same thing we did last time. This is our new Q enclosed. So just plug it into here. We end up over here. Instead of regular Q, we just end up with R equals 1 over 4 pi epsilon naught R squared times whatever our Q enclosed was. The rest was Q, little r cubed, big R cubed. Kill this R squared. Yep. That's just another integral when we do our potential. So for the outside condition, we end up with the potential as a function of R. It's integral from big R to 0, because we're coming in from the outside, of Q R big R cubed and maybe 1 over 4 pi epsilon naught dr. And that's just going to be a number. That's just an R integral. So I think you end up with, let's see here. What are they doing here exactly? So in the solution manual, they get to this step for E. I see what they're doing. So they determine that this is going to be the potential inside the sphere. But then they also say, well, hold on a second. It's the second part to this. You can't just ignore outside. I mean, it's got nothing in it, but outside of your potential is all this charge out here. And so what they do is they set it up as V of R is this guy. Oh, I see what they do. They go to R. That's right. It's going from the surface to little r. Okay, that looks good. Minus on it. So then just subtract off the interval we had before, which is for outside, which is the 1 over, wait, 1 over R squared? What are we doing? Yeah, that's 1 over R squared. 4 pi. Yep, minus the same, which we already knew the answer to. You just subtract that off. I would say that's not really necessary, because this does give you an expression for potential inside the sphere. This will solve out to, what's that going to be? Q 4 pi epsilon naught big R squared. This is going to be R squared over 2. R R. This is going to be the same. Big R's. So it's Q, 4 pi, not cubed, R squared, over 2, minus big R squared, over 2. There we go. Here's your answer. They end up with a 3/2, and the solution manual does a add on this guy, so you sort of have an equation for everywhere. First half seemed to make sense. Second half, body language says makes less sense. So we can try doing it the other way. We start at the center, we integrate out. That's valid too. Problem 6 does that, I believe. In which case, you still get the same ratio for Q enclosed versus total charge. You would go from 0 to little r, and you'd get everything but that big R squared term on the right. And then when you did from to infinity, you would flip some bounds as well, and you'd get a factor of 2 out there. So that if you add the two together, you get the exact same final solution for an equation of V that goes everywhere. You okay? Questions, concerns, comments?
I looked away for a bit, and a lot of the steps jumbled through what the order was.
So, from
part 1, what was part 2?
Oh, this guy's part 1 on the left, part 2 is on the right.
Gotcha.
So I just followed the exact same procedure for part 2 as I did part 1, where we're just going to find E, plug E into our V equation. In order to find E, I need to do Q enclosed. I'd say most of this problem, in terms of difficulty and concepts, is just identifying your two equations that you need and correctly finding what Q enclosed was. The rest really is just algebra and doing a 1 over R or a R integral. You can get set up, you can take it to the end. Alrighty. I was advised that we might benefit from going over a vector review where we do like from a point above a line of charges. We have to do like an integral of everything to find like total E field, some point above the line. Would folks like to do that or do a different problem? We can do it.
What does it say under the lines? It says Q.
Just a bunch of Q's. Yeah,
okay.
A bunch of charges. All right, I'm gonna. Yes.
We can use the point charge equation on this?
Yes. So for here, that's the point charge equation for electric field. Because outside, you only just see Q enclosed. It doesn't matter if it looks like this or like that, or if it's a point charge. It's all the same.
That's how I did it the first time.
Yep. Perfectly valid.
Now I did it with Gauss's law and I got really confused.
Did you get the same answer for outside?
Effectively, but yeah.
Okay.
Just the writing of it was not the same. I couldn't figure out why.
Gotcha. The point charge is the fast way to do it, but the Gauss's law is the always right way.
For what?
For doing any sort of charge configuration, find E and V like equation. Alright, I'm going to erase this board. Okie day. Kaylee was kind enough to give me this one solved out, so I don't have to go dig it out of the old tutorials. Alright.
Is it an old tutorial?
It is
Do
an
you know
old
what one it-
tutorial.
which one it
yes.
is?
I don't know. I
Okay,
don't
that's
remember. It should. I want to say it's like second or third week.
Okay.
Because people were still really rusty on calculus when we were doing it, so it had to be right at the start.
What problem are you trying to do?
We're trying to do the line charge, so integrate along the line from a point P above it.
Which number is it? I think that would have been week 2 or 3 for the
Week 2 or 3.
for E-field.
I feel like it would have been E field.
Jacob, will it be like primarily like multiple choice, like this final?
I think
Like 70%
similar to
multiple
previous
choice.
exams, it would be kind of 50% multiple choice, 50% long answer. But of course, the multiple choice ones go right past. That's the one. Yeah. 3.1.2.
1
This
Yeah.
one. Do you also know how long this test is compared?
tutorial.
It's
Tutorial 2.1.
Like similar questions or
you've got the
longer
full
than
2 hours. Zach, can you confirm whether you guys write it for the full 2 hours or if you write it for shorter?
Our exam.
Yeah, for the final.
The exam will be the full 2 hours.
We're in for the full 2.
final? So it's
But you're in this section.
Mhm.
I don't.
You don't write on my exam, so I don't know for sure.
So
Yeah,
it would
but
be like
I'm
16 or
just
18
curious.
questions.
Sounds about right.
similar length.
I don't get to see the exam until you guys see it.
Okay.
So
So we basically the same time as a typical, same length as a typical exam.
yeah,
All
That's
of
2
the
hours.
it's just university policy. All of the finals are supposed to be 2 hours.
yeah. The other ones have been 2 hours, so it should be the same length. All right. So this problem is let's take line of charge. We're gonna put a point P above here, and we want to find the electric force at P on a test charge.
What does that say?
Find the electric force at point P on a test charge. You guys might remember back when we were doing test charges, there was some confusion about like, well, does it like make its own electric field? Do they interact? We don't have to worry about any of that. Basically, find the strength of the E field, then just plug it into the force equation. So I want force electric. The equation I want, F equals Q E plus V cross E. Dundee. So we just need QE. So we just have to find E field.
Wait, there's no B.
No magnetic field. We just got some.
This is chapter 3. We didn't do magnetic.
Yeah. We didn't touch magnetic field at chapter 3. So the way we.
So you just times like Q by E.
That's it. That's the great part about electric field. It's easy to find. Or electric force. Easy to find. Just like gravity force. You just multiplied M by the gravity field. So we need to find E. But we have some definite configuration of charge. So we're going to have to do an integral. Okay. How are we going to set this up? Well, at some point, I'm going to have some small amount of electric field we're going to produce. That is going to be determined by K, Q over R squared, R hat. That's just electric field from a point charge. Now we're doing a little bit of E, so I did DE, so we're going to use DQ. Right? All I did was take what the regular equation was and make it infinitesimal. I could have picked DR instead of DQ, but I picked DQ because As it turns out, dr gets really gross. I'll try to do the problem that way. So if we start getting lost in the soup, stop for a second, pick a different variable to infinitesimalize. So what is going to be dq? Well, it's going to be some amount of charge here, dq. And this is going to cause our d. Okay, so what is dq? Well, how much charge is in here is going to be essentially the density of charge on this line divided by times the amount of area we're looking at. So what I need is the charge density, which is lambda, times whatever area this is. This wire we're going to have, it doesn't have a real thickness to it, so we're just going to call it dx. We're not going to know that sort of dy. This is the charge density times length. That'll give me total units of charge, because charge per length times length. Notice this is really similar to how we just did Gauss's, where you set up the density times the amount of stuff you're looking at in order to find the total. Okay, that's just an equation. We can just plug it in over here. So I've got that dE equals k lambda dx, or r squared in the r hat direction. Okay. We're in Cartesian coordinates. R is kind of inconvenient here. If we had like an arc of charge, we could keep it in R, because the R would be the same. But R is going to change as we sort of sweep through here from the perspective of P during our integral later. So we need an equation for R. Okay, so we can do that. That's going to be, this is R. Okay. So R squared equals x squared plus y squared. It's just a triangle. Now, fortunately, y doesn't vary at all, does it? We're going to keep y the same, just sweep through x is the main goal. So I'm just going to label this y naught. It's just a number. We'll probably pick 0. That seems like a nice value for y to have. But we'll leave it as y naught for now, so that we could do the problem at a different height. Plug that in here. We got that dE equals k lambda dx x squared plus y naught squared r hat. Hey, there we go. Now we've got all the same variables going on. Great. So we could integrate with respect to x now if we wanted to, because we've got like a x dx type equation. We couldn't integrate before because r and x weren't the same variable. What I'd like to do is either integrate through x, or I could integrate kind of like sweeping through here. I could integrate through theta. It's kind of my choice. I'm going to choose make sure I'm consistent with the tutorial. Let me pull up the tutorial solution. What are they doing there? For 3.1.2. 3.1.2, I see, okay. Yes, okay. So I got this equation here. K dq r squared k lambda d squared plus x squared. Yep. 1/2. Yeah, okay. So I'm going to choose to sweep through theta. So I need to express in terms of theta what my e's would be. So in terms of theta, my different reasoning actually. This, if we integrate this up to find e, will give us the answer. But it's going to give us a vectorialized answer, so it's a vector integral. And I hate vector integrals. This whole class has been about how to kill vector integrals and cheat, right? So let's not do that. Let's find one component at a time. Let's pick the y component. In which case, if we only want y, then the y that we want is going to be our e times what do we do? Cosine theta. We're going to do this theta. You could pick a different theta, so cosine might switch to sine. Just depends how you define your personal angles. Okay, so if that's true, then if we infinitesimalize it, it will be 2. Well, now all we have to do is just write out what cosine theta is. dE times what's cosine theta? It's opposite over adjacent, or opposite over hypotenuse, so y over r, y over x squared plus y squared. Great. And of course, those are just constants, so just y naught. Okay, so then dEy equals dE k lambda over x squared plus y naught squared dx times y naught over x squared plus y naught squared. Looks right to me. This might have to be rooted. Yeah, this is r squared dot r. That's rooted. Question?
I was just going to help you out with that.
Thank you. Great. So we got the square root here, the full term there. You can scrunch that together. It's a 3 halves. On the bottom, we get k lambda y naught over x squared plus y naught squared with 3 halves dx. That's even worse. Come on, lambda. There we go. And that should match up. Beautiful. Okay. That's an integral. We can do that integral. Let's do it. We just want to run from the start to the end, so whatever the length of our rod is. I would say, let's just define it as plus L to minus L. In which case, EY equals K lambda y naught integral from minus L plus L of x squared plus y naught squared minus 3 halves dx. It's an integral. You do the integral. I think you get a 3 halves will come out. Maybe a minus 1/2 left over. And you have to divide by minus 1/2, so we get a factor of 2. So I end up with a 3, basically, up front. I think once you plug and chug everything, which I'm going to skip for brevity, you get 2k lambda L over y naught squared plus L squared 2e 1/2. Tell me it's 1/2. Yeah, 1/2. The y component of the E field. If you want the x component, sine theta. Same idea. Integral gets a little more nasty because you end up with an x on top. Once you got E, plug, multiply by Q. Done. You got it. Yes.
So F just equals that times Q.
That
There's
times
no
Q?
Q in the numerator.
That's literally it. This problem is a really good practice of looking at a charge configuration and setting up an integral and finding a bit of a disaster in bookkeeping. Being like, oh god, can I take my integral yet? No, I have to replace r with x because it depends on x. It's good practice. Do I see a hand?
Me?
No?
No, I'm good.
Cool. Other questions on this one? Let's see, anything else in the notes? Bulb addition problem number 6 is in the notes as well. Do folks want to go over that one? Yes. Okay.
Which one?
It's number 6 in the practice exam. So I'll actually just do it all the way over here on the left. Battery. Okay. So problem 6 just asks, hey, if I have just this series of 3 resistors, I turn on my circuit, they glow. If I add in this right branch, what happens to the brightness of these guys? aka, what happens to the power that they consume? All right. So intuitively, let's think about what we know. The voltage drop across this branch and that branch is going to be totally identical in all these situations, right? Because you go from all voltage to none voltage. So the voltage drop across this isn't going to change. So I've got my Ohm's law, V equals IR. I want the power, because I want the brightness, which is, I believe, I times V. So I know V is not going to change at all when I add in this next parallel resistor. But I'm not so confident, because now I've got this split current at my junction. I should probably run the math. So let's work through the math. Before, what we had was a net resistance of 3R. It's 3 resistors in parallel. R effective equals 3R. When I add in my second resistor, parallel, 1 over R effective equals 1 over this branch plus that branch. Okay, that's going to be 3R. I'll multiply this by 3 on both sides. We get, 4/3 R. So we get RF equals 3/4 R. Because we get 4/3 we have to flip. So I can use that to find the total current going into my circuit. So I know what V is, it's just V. So then I total equals V over 3/4 R. Which is going to be 4. It just works the second hour. Oh, my brain's stopping. V times 4 over 3R. Okay. So that's my total current. If I think about the current that has to go into each of these 2 branches, I know Ohm's law is key. So on this rightmost branch, I'm going to drop as V equals IR. So that means I have to drop all of V through 1R, so I'm going to get 1I. So this rightmost branch, V equals IR, so I just equals V over R. But on this leftmost branch now, it's V equals IR. 3R is what's on this branch. So I equals V over R times a third. So here is my current that flows through the middle branch now after I've added my additional resistor. I just have to compare that to what was going through it before. So if we go back to before, I knew that R effective was 3R. V over 3R equals R. Equals IR. Oh, oh, those are identical. It's unchanged. Questions on process in that? Just find your initial current because you know V and R effective. Then tack this guy on, solve the circuit again. This is why, by the way, that all your lights in your house and in your Christmas lights, they're wired in parallel, so that it doesn't matter how many lights you add; they're all the same brightness. Note, of course, that I total was larger after we added because these guys pull the same power, so you just have to add more draw from the battery each time in terms of current. But in each individual branch, they basically ignore the other ones. Makes sense. A lack of confidence, yes. Okay. Think about it. Brew on it. Ask us another question if it comes up. Those are all the noted ones. Other problems people would like clarifications or help? Yeah.
Can we do a mirror one?
Sure, we can do a mirror one. Yeah. What do you want to do? A convex or concave mirror?
Whatever.
Let's do them both.
We do the one that's in the practice problem.
Sure. Which one is that?
18.
18. Zhoo. 18. That's a lens.
Oh, sorry.
I mean, we can do a lens, but let's do the mirror to start. So, we've got our optical axis. We're going to have our object. We'll start with a concave mirror. We could be asked to find, say, object height, object distance type information. That would give us magnification too. So, first thing we're going to do is ray diagram. This has some focal length. I'm going to call it that. So, when we draw a ray diagram, because really these optics questions are always ray diagrams. It's the same way as when you're doing force diagrams. You draw a force diagram. You can't get away from it. Fortunately, if you use the tool, it always just solves it for you. So, 3 rays. We've got the parallel ray. We've got the focal point ray. And then we're going to have just those two for the mirror. If we had a lens, we could also do the midpoint ray, but it's a mirror, not a lens. If something comes in parallel, it leaves through the focal point. If something comes through the focal point, it leaves parallel. Where they meet, that's your object. For the math, we use the same equation that we do for the others with the lenses, which is, oh geez, I have to relook at the lens equation. It should be something like 1 over P plus 1 over F equals, 1 over I equals 1 over F. The I is your image distance, so that's going to be this guy. F is your focal distance, this guy, and P is your object distance, or it could be O. Personally, when I draw raised diagrams, I have to draw them like that, so that it's a big P arrow. That helps me remember that it's P. Plug in the numbers. Whatever you're given, plug those in. Should be able to solve for everything else. It's possible that you're given something like magnification, in which case magnification is your initial over your result over your initial. So how much you improved, which also equals I over P. I think they throw a negative on there. Yeah, they throw a negative on there because it's inverted.
It's also valid to use. I usually do O and
I like O as well because it's object.
Right.
Yeah.
So just as long as you're consistent about using either O and I or P and I everywhere. It should be fine. Is P supposed to stand for something? Is it just principle?
So we actually ran out of O's to use when we went from mirrors to lenses. So they said, oh, you know what? We'll use the next letter. P. That is legitimately the reason.
What do you mean we ran out of those?
When they were doing optics, we used O, we used whatever the Greek letter O is as well. It's not theta, it's not omega.
O is
Omicron. I think we used it.
like an O.
I think we used them.
That's of course that's why.
Do you want me to go deeper into this, or is this sort of just like?
So you go deeper if you want.
Well, I don't really know where the gap. Was this all familiar and confident?
Sure.
Sure. Okay. So we can do the exact same thing with a convex mirror. In which case, we've got a parallel ray and a focal ray. If something comes in on the focal, it comes out parallel. And if something comes in from parallel, it goes on the focal. Now, how did I remember that they go the other ways? Because I just thought about it reasonably. This is a mirror. You have to bounce off incoming, outgoing. They just have to be equal. Same with down here. So that's kind of hideous. Doesn't really seem to make an image. Until You got to do the imaginary image. So once you draw your lines, just start extending them dotted line wise until something intersects. That'll be your image. Exact same equations apply. But it's up to you to remember who's inverted, who's imaginary, based on your lens diagram.
Like the last part, we started going like crazy.
When he was like moving the image.
Should we like spend a lot of time on like getting those drawings down, like making sure we get the rays right, or knowing like the overall conceptual like visual versus like virtual versus real?
Would it be multiple? Would it be like multiple choice?
I would suggest against just trying to memorize like if you have a convex mirror and you have this inside the focal point, then this happens, because there's just too many options. Like there's a mirror and then inside the focal point there's a lens and then inside the focal point. There's too many.
So just go with like the basic two, like what you know about convex and concave mirrors. Like,
Yes, and how to draw the ray diagrams.
okay.
Because the ray diagrams will save you every
And
single
then how
time.
to do the math to solve them.
Yeah, the math is honestly I think the easier part, because you have the equation sheets and it's basically just those equations. I'm not going to say easy because it's not easy. None of this is easy, but yeah. So the ray diagrams, it's really just getting practice with drawing them. Okay. So what have we been doing? We've been working on like 14.2.
We did problems 4. We did like another problem, little vector problem, and then we did just 6.
We did one tutorial.
And a short problem, and then the mirror problem.
Okay, so what do we want to do?
It's the hardest question.
Can we do a lens?
Can we do either 17 or 18?
18.
Yeah, let's do it.
I'm sorry.
I don't know what 17 is.
17 just has a lot of words.
Let me read. Is 17 the one with like the power over intensity?
It has like a pool.
Oh, yeah, we can do that one.
So-
Snell's law.
Oh, wow, you know Snell's law.
I believe it's Snell's law.
Is it
Actually, somehow got this point.
one side, one
Mine
side, two
is
side,
in
two.
last semester.
Okay.
If I can do it again, then I'm gonna be great. I'm not gonna do it anymore. But I got it right. Something.
Yeah, mine was
But
first
we know it's a good. Snell's law is going to be on. Because half the exam is just going to be
Yeah.
a quarter of the exam.
My friend who had that exam just said that he
Okay.
had multiple choice. I'm like,
So I believe that this is like water,
New stuff.
Yeah.
right?
Oh, and half of the stuff is object.
And this is air.
Yeah. So a quarter of the exam.
I see where you're.
So 2 questions with optics out of 16.
He said that there's 2
Believe I tried.
with least, one with ray diagrams, one with math. I expect this actually.
Okay.
I think that's third person. I'm imagining one that's like one that's
You should know this.
You're gonna get the same for me?
That would have been those back.
Well, we'll be back.
That's
Last 3 things we learned.
Because you know that's everything.
No, I think yeah. It's kind of worth it.
Actually, I'm wearing a lot of it. I like this.
When you see the ball underwater, it's not where you think it is in waterfall. Think
Aren't
about
all
it.
the exams
I
like
mean, I guess,
like
but the
40%
ball
of us is
floats.
0? You know what I'm saying?
Yeah,
Can
so
you put it underwater?
So
Can you still put it underwater?
No, it's turnover.
encourage
That's actually a strategy, though. If you push them onto the ball to push the ball under, they
Oh, it's been
push the
holding
ball
us.
under, and then they get the penalty.
Because you can't. Oh, you can't hold the ball. It's a tutorial about
So there'll be some absurd exam questions.
Just swim with the
That's
ball.
like
Just do whatever
really
you want with the
niche.
ball. You just can't, like,
All the
put it under water.
You can't hold it with your legs.
This question from
This
lectures, I think is a quick do.
Okay.
I don't know.
I think optics is
That's
probably
all.
one of my favorite parts this semester.
That's bullshit, dude.
The most.
Okay.
I used to think that I understand most studying electricity.
Yeah. I don't necessarily.
What was the question?
I like the circuits because I thought it wasn't that hard.
No, that's my first.
Magnetism.
All right, let's come back together. So this problem, it starts with a light source that's inside the water. And then the light source there's 2 rays I think that you're given in the problem, potentially, yes. There's one that intersects the water air boundary perpendicular, so it's like a 90-degree angle. And then there's one that has an angle of incidence of θ1 at the water air boundary. Okay, so, and then it's asking us to solve for D, right? Determine, determine the apparent depth. Okay, so it's asking us to solve actually for this D. Okay, does it show you what, oh yeah, it gives you what D is. Okay, perfect. Okay, so anytime you see light rays interacting between two different media, you should really be thinking Snell's law. So Snell's law, just write it out. And I want to make sure I write these things exactly how you see them on your formula sheet. So can somebody tell me what Snell's law looks like? Is it N1 sine of theta 1?
Yeah.
Okay. Equals N2 sine of theta 2? Okay. So what Snell's law actually means is the index of refraction of the medium that you start in, your light ray starts in, times the sine of the angle of incidence between your first medium and your second medium, so in this case it would be theta 1, equals the index of refraction of the second medium you end up in times the sine of the angle between the vertical and your new kind of ray, light ray. So that's what theta 2 symbolizes here. Okay, so are you given theta 1?
No, so
Okay, so you were solving for theta 1. You're given theta 2. Okay. We also are given N1 and N2. So N of water is, I believe, 1.33. N of air, so this is N1 because we start in water, and N2 is going to equal 1.
Are those that given to us and memorized?
I would memorize this. I would memorize that index of refraction of air is 1 because I'm not sure if that's given. This will probably be given. So now let's just go ahead with Snell's law and see what we're missing, because what we're probably going to have to do is solve for that missing variable first. So I'm going to plug in N1. We have 1.33 sine of theta 1, which we're not given, equals N2, which is 1, times sine of theta 2, which is given 5. So I'm just gonna. Is it 5 degrees?
Yep.
Okay. Okay. Full chase is just kind of plugging in the known variables. Okay, we see that we don't have a theta 1. So you should probably be thinking, I should probably solve for that. Theta 1 is equal to, I'm actually going to do this step by step. So sine of really, really big theta 1 for no reason equals 1 over 1.33, just dividing 1.33 over to the other side, times sine of 5. To find theta 1, I want to take the inverse sine of the right-hand side. So I'm going to say theta 1 equals sine inverse of 1 over 1.33 times sine of 5 degrees. Okay. How do we feel up to here? Not bad. Okay. So now it's just a little bit of geometry. So we've solved for this variable here. We know we're trying to get this variable. So what we can do is we can essentially solve for our variable x, which is going to take us between this triangle and this triangle because they have x and y. Do we see that? Kind of. So in order to do that, I have two known variables for this triangle here, and I'm actually going to highlight it. We've got this triangle here, where we know theta 1, we know x, and we know the height, which is big D here. Right? So I can solve for x in terms of my new known variables. When you do this guy out, you should get an angle of, and check this because who knows, they always get these things wrong, 3.76 degrees. Did people get that? Okay. So now theta 1 is a known variable, equal to 3.76 degrees. D is given in our problem. X is something we can solve for. So let's try that. So in terms of theta 1, I can say tangent of theta 1 equals opposite over adjacent, x over d. How did I know to do tangent? I could have done this hypotenuse if I wanted to like do Pythagorean theorem. It's just an extra step. So I would say if you have two known variables and they're the opposite and the adjacent sides of the triangle, probably you're doing tangent, right? So let's solve for x. X equals d times tangent of 3.76 degrees. D is given, big D, 2 times tangent of 3.76. And what do we get?
1.1.
0.131?
Yeah.
All right, I'm taking that. To be true. Okay, so after I solved for x, now what I can do is I can backtrack and say, okay, well now I have information about this, which is ultimately the triangle that we're interested in because we're trying to find this apparent depth, d. Okay, so now I can say, well, I know, let me just make sure. Yeah. Yes. Okay, so I can say, let's use this exact same kind of thought process to solve for my d variable now. So I know, I think that they use theta 2 is equals d. Tangent of theta 2, which would give me, okay. So they kind of redraw this triangle. This is kind of like a throwback to force diagrams, if you remember those. So all they're doing is because I have this theta 2 variable here, I know that that theta 2 is the same as this angle here, right? Do we see that? Do we remember that from our geometry? I must hit geometry class. So these two angles are the same. I'm trying to search for this height, which is just the same thing as drawing perpendicular there. This guy is d as well, and this guy is x. And now I have an angle to reference, which is angle theta 2. Do you see that? Kind of. Right? So now I can do this exact same thing, but for theta 2. I can say, all right, let me take my tangent of theta 2. And I'm going to set that equal to my opposite side, which is x, over my adjacent side, which is d. Little d this time. Okay? So I'm going to multiply both sides by d. D 2 equals. Nope, I'm going to multiply both sides. Hang on. I'm going to multiply both sides by d and divide both sides by tangent of theta 2. So I get that d equals x over tan of theta 2. We found x here, 0.131. Dividing that by tangent of my theta 2, which I believe theta 2 is also given, right? What is theta 2? Okay. So when you do that, you should get 1.5. So they leave everything in terms of variables until the very end. That's totally fine. You can do that if you want. But this is also totally valid. It's solving for what x is and then just plugging in to the new formula. So I would say the hardest part about this problem is this geometry that goes on inside here, right? So if we want to just blow this up really quick so we can actually see exactly what's happening. If I have theta 2 here, I'm going to, let's see, here's my light source. Wait, here's my light source. Got a perpendicular ray going like this. I've got a refracted ray going like this. So the part that matters, right, is if I'm an observer outside here and I look at these two rays coming out and towards me, the image from that ray, I can basically, remember when we're on the whiteboards back tracing these rays? That's essentially what I'm doing. I'm going to say, okay, this one back traces back, and then this one also back traces like that. So that's essentially where I think the object is, right? Based on this refracted ray. Okay, so this is the apparent distance, little d. This whole kind of big triangle is big D. Where the geometry comes in is, okay, if I'm trying to figure out where is this theta 2, but with respect to this little triangle, I can say, well, let me just kind of flip and mirror this little triangle. Just for convenience, because now, hey, look, that's theta 2 right there. You can also do, if you'd like, 90 minus theta 2 and use this as your reference angle. That's also completely valid. Okay. Questions on that process? So if you went this route and used 90 minus theta 2, you would just flip what you have. So you'd have, for your tangent, you'd have d over x instead of x over 2. But then again, you'd flip them around, so you'd get the same value. Okay. Questions on that? No? Feeling decent? Cool. All right, next question. Oh, tell me that's not that. Oh, okay, no. Oof. Okay, this one we can do. The AC circuit, I was like, what? But we can try. Honestly, I think that is just going to be mostly memorizing those formulas and really just knowing what, not memorizing because you have the formulas. It's just utilizing those formulas and knowing what impedance is. Yeah, because impedance for an AC resistor is essentially just resistance for a DC resistor. So V equals IR acts the same way, except now you're using impedance Z instead of R.
Impedance is like the Z equals square root of.
Yes. Yes, exactly. Yep. Yeah.
Phaser. When did we go over that?
Did we talk about phasers?
You didn't tell me.
Because it's on what you should know. And I was reading that and I was like, did we ever speak about that once?
So I don't remember doing that.
Okay.
Phasers.
There was no choice in the exam.
It's a ton.
Jacob said it was gonna be half multiple choice, actually.
Our filter
This
says
girl's final said no multiple choice.
That was
And this
the
was your professor too. No.
Was that?
Stupid explain.
Wait,
You're
that
class,
was
yeah.
your professor.
I think that's how I get it.
Oh,
It's like,
Well, he does have office hours.
it does depend on the professor though.
Phaser
Remember
diagram.
like last semester I didn't have multiple choice, but my friend did have multiple choice for her. She had to professor.
somewhere.
Oh, 14 or 17. Okay.
Wait, he has office hours right now.
And this semester was on Tuesday.
No, the Mondays, usually after class at like 2:30.
I don't even remember doing phaser. If you guys can find a phaser problem, we can definitely do it.
I also went. I feel like it's too late at
Like
night.
we learned it.
Yeah, that's kind of, that's how it goes.
Seems seven.
All right, so you wanted to do 16?
Because actually,
Yeah,
don't
I think
consider
it's
them
the hope-
two certain amount of problems.
Yeah, it's not too bad, but it's a good one to go over. All right, let's go over question 16, problem 16. Can I erase this guy? Yes. Yes. Are you guys killing those? How many are there?
It's like 20 left.
Okay.
You want it?
There's 2 more.
Bro, do you want
Yeah, no one for the jellies.
I was joking.
I'm like,
Kind of some shit. Julie's one.
You want it? Why?
Okay, problem 16. So it says, when you look at the North Star Polaris, you intercept light. All right, everybody, let's come back together. You intercept light from a star at a distance of 431 light years and emitting energy at a rate of 2.2 times 10 to the 3 times that of our sun. Okay, neglecting any atmospheric absorption, find the peak amplitudes of the electric and magnetic fields when the starlight reaches you. Okay, so I guess the hidden kind of language that they're using here is peak amplitudes. So peak amplitudes will be these variables, E0 and B0. This is the peak amplitude of the electric field. This is the peak amplitude of the magnetic field. Okay, so there's your secret, you should be underlining peak amplitudes. Then your brain should go, okay, these are the variables I should look for on my equation sheet. When you look for those variables, you should find that intensity has E0 in it. It has 1/2 C epsilon naught E0 squared, right?
Yeah.
Okay, so that should kind of be a telltale sign, like maybe I should be looking at intensity when I'm approaching this problem. That's the biggest leap in this problem, is figuring out it's talking about intensity. Okay, so from there, let's see. So it says, source is so far away, it emits light with equal intensity in all directions. We know that. The intensity at any distance r from the source is related to the source's power. Okay, so another formula that you have for intensity is power over area. No. Yes, power over area. Okay, the area that we're talking about is the area of the surface area of a sphere, right, at some distance r. So what we're using here, this is essentially power that our source gives off over the area that's receiving it, which is the area of a sphere, surface area of a sphere, of some generic radius r. Okay, we have two equations for intensity. I equals this, and I equals this. So what does that say about this and this?
You can set them equal to each other.
They're equal. They both equal I, then they both equal each other. Okay, cool up to here. Okay, so what did we say we were looking for? Peak amplitudes, E0 and B0. Now I have an equation where I can solve for one of those variables. I can solve for E0. So let's do that in terms of the power of the source. So E0 squared, I'm going to multiply both sides by 2, so I get 2 P source over dividing both sides by C times epsilon naught, and then 4 pi r squared. Okay. I'm going to square root both sides to find my peak amplitude. So E0 equals square root 2 power of the source over C epsilon naught 4 pi r. Okay. Plugging in, because we're given weird units, we're given units of light years, we need to do a unit conversion, which stinks, but let's do it. I'm going to go over here. Okay, what are you given here? Okay, so are you given the conversion factor? Yes. Note 1 light year is 9.461 times 10 to the 15th meters. Okay, so 1 light year. We want to convert light years to meters in order to have everything in SI units when we plug into this equation here, because this equation assumes all SI units. Okay, so how do we do that? Well, we're given a conversion factor. 3 point. Okay, so they're doing C times. Okay, so they're doing the speed of light times a year in seconds. Okay, so it's 3.0 times 10 to the 8. This is in meters per second. Then we're multiplying that by seconds to find meters, right? And the seconds that we're multiplying is the seconds in 1 year, because that's the definition of 1 light year. It's the distance for light to travel in 1 year. So light to travel in 1 year, we need 365 days, 24 hours in 1 day, 60 minutes in an hour, 60 seconds in a minute, and that's it. Do we understand that conversion? Kind of. Okay. And when you do that, you should get that 1 light year, which is the distance, is 9.4608 times 10 to the 15th meters. Again, I would do that out, because who knows with these answer keys? Did anyone do that out and actually get that value?
Yeah.
Okay, beautiful. Okay, so now everything that we have is in SI units, so I can just plug and chug, I believe. So I'm plugging this value in for, what am I plugging for? Yes. Yep. R. So I get E naught equals square root of 2. So I'm going to give you something related to power.
It's given.
Okay. 3.90, that one. 0 times 10 to the 26 over C, 3 times 10 to the 8th. That's in SI units already. Meters per second. Epsilon naught. That's a value. I don't know what the value is. Does anyone know?
We have a question.
Yep.
But it says radiant energy at 2.2 times 10 times the sun.
Cool.
Multiply that by 2.2.
Thank you. Times 2.2 times 10 to the 3rd. Thank you. Okay. And then epsilon naught is also just some value. Just make sure that you're putting it in SI units, because this equation wants everything in SI units. And then times C epsilon naught for pi. And now R is what we solved for. This is a distance. Was this supposed to be 10 to 15? Yeah. Thank you. Square. Okay. When you do that, what do you get? Did anyone do that out? You should get 1.75 times 10 to the negative 3rd. To the negative 2nd. I believe you should get it. So this is what it says it's equal to. 7.75 times 10 to the negative 3rd. Definitely keep checking. Make sure your parentheses are in the right places when you're plugging it into the calculator. It's the only thing I can think of.
It wasn't red, so
What?
Big enough.
Was it just not close at all?
No, I didn't even get it.
Oh,
I was
okay.
typing it wrong.
Oh, okay. Yeah. Multiplying this by 431?
Yeah.
Probably. Oh, 100%. Okay. Okay, yep, that's what it is. I'm forgetting all of these factors. Okay. You intercept light from a star at a distance of, it's not 1 light year, it's 431. Okay. So this value inside the parentheses should be multiplied by 431. You guys are saving me. And then this whole thing is squared. Okay. That should give you this value. Okay, cool. Then all you need to know is the conversion between E naught and B naught, because it also asks you for the peak amplitude of the magnetic field. So we found peak amplitude of, I'm going to write that it's called peak amplitude of the electric field. We want peak amplitude of the magnetic field. And that conversion factor is literally just C equals E naught over B naught. Are you given that equation on your formula sheet? Okay, beautiful. So once you find E naught, it's really easy to find B naught, right? So I'm just going to divide E naught by C. When you do that, you should get 5.8 times 10 to the negative 12 Tesla. Okay. That was a little rocky. Do we understand kind of what's going on? Sort of kind of. Tesla is the unit for a magnetic field amplitude. So that's almost just, you can just find, okay, well, E naught is in volts per meter, or you can leave even volts in SI units, and just, things will cancel out and you'll get something equivalent to Tesla. That's completely fine too. So even if you don't, for lack of a better term, like simplify your units, that's totally still valid for an exam. Okay. Questions on that? I do want to mention there was one question, I think it was like a tutorial question, that was talking about light intensity with like a different area. Did you guys see that tutorial question? I can try to pull it up. Well, it made absolutely no sense. So if you get to that question, the verbiage that they used was just like incorrect. So don't worry, I would honestly use this more as a reference than that tutorial question that we were trying to have you guys do, because it didn't make sense. I had like 3 TAs working on it and we were all like, what are you talking about? So, okay. Cool. Any other questions? Have you guys like thrown it back to original material very much?
Do problem 9.
Yes. Problem 9. Okay, this is a good problem to do. All right, so if you need pictures or anything, take them now. What's that? Problem 9, I believe you guys had something similar to that on exam 2, maybe, or exam 1 for Belter's class. So problem 9, we have this configuration. We have -1, 2, A, B, C. Then we have 1 wire. Another wire. There's some very same magnitude of current, which is I. And we're asked, what is the net magnetic field B at points A, B, and C in the figure below? If we're given that I is equal to 10 amps. So this is like bringing us back to like right-hand rule situation. So if we want to find the direction, this is how I always start these problems. The direction of the magnetic field about a wire, we're going to use our thumb and point it in the direction of the current itself. So if I have a dot that's coming out of the page at me, my fingers curl in the direction of the magnetic field. So I know the magnetic field lines about this wire look like this. Right? So they're going counterclockwise. Similarly, for this guy, I'm going to point my thumb in the direction of, or into the board, so in the direction of the current. My fingers wrap around in the direction of the magnetic field. So we've got a B field here that goes clockwise. Okay. Cool. So let's first deal with point A. So where my B field intercepts point A is important. So another way to say this and actually show this that I find really helpful is if I draw the radial distance between my wire, the center of my wire, and my point, my B field at this point is going to be perpendicular to that radial distance. Which means it's going to be perpendicular for this one, perpendicular and down. For this guy, it's going to be perpendicular and up, right? So if I had to draw the B field at this point due to this wire, it's going to be a line perpendicular to the radial distance between them. And that's my B field due to this first wire, which I'm going to call I1 and I2 just because I think it's going to pull. Even though they're the same, we'll plug this afterwards. So this is I1 on A. Okay. Similarly, we know that this guy creates a B field up and to the right, perpendicular to the radial distance between them, which means it's going to actually follow this path, and we'll see why. So this is B due to I2 on A. Sorry if you can see that, but you know the vibes. Okay, cool up to this point. How we draw those vectors, because that's important.
Could you again outline where the B, the last one you just did, B?
This guy?
That? Yeah.
That's B I2 on A. So the B field due to I2 on point A.
Oh, gotcha.
Cool. Okay. Cool. It's asking for the net magnetic field. Just from this diagram alone, because we know that things are symmetric about the x-axis, we can tell already that the y components of these two vectors are going to cancel out. Do we see that, or do we want to go more in depth on that? So these are both, just to make it a little bit more clear, these are both 1 unit out and 1 unit up from point A, right? They both have the same magnitude of current, which means they have the same magnitude of magnetic field at any point around it, right? So at point A. So what that means is that after we draw these vectors, so how each B field is interacting with point A, this component of bi2 on A and this component of bi1 on A are going to be equal and opposite because of the symmetry of the problem. If I was to take this and move it a little bit down, they'd be different. If I was to change I2 to be a lesser value than I1, they would be different. But because I's are the same and the distance between point A and each wire are the same, it means that those two should cancel out. The two Y components should cancel out, right? One's going up and one's going down. Okay, so that simplifies our life. All we have to deal with are the X components. What do we know about the X components of these two V fields? If it's the same magnetic field, or if it's the same, oh, I gave it away. If it's the same current and it's the same distance from A, we know that the magnitude is the same, which means that the magnitude of the X component is the same. So I'm basically getting two components of my V field that are just the same component added together. So also simplifies our problem. After I solve for the X component of one of those B fields, I can just double it. Cool? So let's do that. Okay, so we need to, actually, I think I broke this one. Their solutions are not so good. What problem is this? 9? Oh, I just drew an incoherent diagram. Okay. So let's do the magnetic field. Let's see. B. Oh, yeah. We're going to do B. Let's do I1. So the magnetic field that I1 causes at point A. So you're given a formula that says the magnetic field formed by a current carrying wire is mu naught I over 2 pi d. Are you given that as a formula?
Yes.
Okay. No? Is it? Yes, okay. Okay, this distance is talking about the distance between your wire and the point of interest. So in our case, this distance is going to be the distance between I1 and A. Right? So it's going to be this radial distance that I drew in green. Well, how do we find that? Well, if this is 1 unit and this is 1 unit, then we can use Pythagorean theorem to say that the hypotenuse is equal to the square root of 2. So just to break that down even more, c squared equals a squared plus b squared. 1 plus 1 equals c squared. Take the square root of both of those, and I get c equals square root of 2. Okay, cool. So I know that the distance that I'm going to be concerned about is the square root of 2 distance, the distance between my A and my I. But then again, like we said, I'm only really concerned about the X component, right? I know that the Y components cancel out, so I want the X component of that magnitude. Okay, so this is where they kind of get you a little bit. The X component of this magnitude corresponds to this guy here, which if I have to draw it like this, if I have a 1, 1 square root of 2 triangle, I know that my angles here are 45 degrees, or pi over 4. Do you remember that? It's like unicircle kind of stuff. So this angle, theta, is pi over 4. So what I can do is I can multiply this by the cosine of this angle, because it's the, wait, is that right? Sine over that. Yes. Yes. Say cosine of pi over 4. This is also kind of similar to those force diagrams that we were doing. Just dropping things down and multiplying by either cosine or sine of the angle between them. Do we see that? Kind of? Okay. So this gives us a component in the X positive, etc., which is also positive I hat. But we can just leave it like that. They seem to be doing like a whole bunch of other things, but I think that they just cancel out. Yes. So where you see it, like that negative sine pi over 4 plus sine pi over 4, we already took care of that by saying those two cancel out. Right? Yeah.
It says here that it's 2 cosine of pi.
Yes. So that's coming to my next point. Okay. So what did we just do? We just solved for the x component of the magnetic field caused by one wire. We have 2 wires. And they're equal magnitude of the current, which means they create equal magnitude of B field. So I can just reason my way through this. Okay, if I have 2 instead of 1, they're both at the same distance from my point, and they both carry the exact same current of I, then their x component, the x component is going to be exactly the same, right? So B total at point A is equal to B I1 A. This is always so annoying, but I'm just going to write x component of this guy plus B I2 A x component of this guy. I know B I1 A is equal to x component is equal to B I2 A x component, which means B total at point A is just 2 times what we found here, B I1 A in the x direction. 2 u naught I over 2 pi d we found to be square root of 2 times cosine of pi over x half. Okay. How do we feel about that? You can brute force this and just like find the y component due to this guy, find the x component due to this guy, which is what they're doing in the answer key, and then do the exact same thing here. But you have to kind of get into the mindset of exploiting symmetries in these problems, because it is going to save you so much time on exams. So I believe it's pretty much the exact same kind of setup for B and C, although now B is going to have the perpendicular component, so I'm going to actually draw. For B, the radial distance between my wire and B is like this. So this guy's going to point directly to the right. This guy's going to also point directly to the right. It's going to do the exact same thing. Their x components are going to add. They're going to be equal, so it's just double one of their x components. And this is also, I believe, going to do the exact same thing. This is down and to the right. This is up and to the right. So their y components cancel, their x components add. So you're just doubling one of their x components. Okay. How do we feel? Yeah.
For B, it like confused me that there was only an x component because like intuitively it looks like it's just y. You know what I mean?
Yes. So if you do what we did here, where we draw the radial distance between them, right? So between the wire and the point, and you say the B field has to be perpendicular to that radial distance. The only way it can be perpendicular is if it's directly in the X.
So we really have to draw out that.
Yes.
Okay.
And I don't think they ever really had you drawing that distance, but it's so helpful.
Yeah, no, that helps.
To draw that.
I know that was a thing.
Yeah, to draw that R vector is really, really helpful.
Okay.
Cool. Okay. Do we want to do the other ones, or are we feeling pretty comfortable? So the only thing that changes for B is the distance between them. And yes, the distance between them. Okay. Yeah. Questions, comments, concerns?
The angle would be the same for B.
You don't have to worry about the angle now, because it only has an x component. Sorry, that is a good point. Yep, so you don't even have to be multiplying, yes, it does.
Okay.
Don't have to be multiplying by cosine factor, because it only has an exponent.